Okay, so this is the walking talking mock for the P4, P5 and P6 exam. First thing you notice, on the second page you've got your equations, and you're essentially going to be looking at explaining motion, electric circuits and radioactive materials. So there's quite a lot in explaining motion. That's where any confusion is likely to occur. So our first question, Iggy the cat, who calls the cat Iggy, sitting next to the bottom of the wall. First question, 1 mark question. So jumps from the ground onto the wall. So that's important. Okay, the wall's 1.5 meters high, and you gain 66 joules of gravitational potential energy. So because we've got height and gravitational potential energy, we can probably work out which equation we're going to use. Now, what I don't like with these OCR questions where it's a calculation is the fact that we've just got to ring a right answer. I would put some working out over here, because in this one you're probably going to have to rearrange the equations. So if you try and do that without any working out, you're probably going to make a mistake. So I don't know which method you prefer, but if you use a magic triangle you could draw it, or if you just write the values, etc. But make sure you do some working out, don't leave it to chance. Part B, as he walks along the wall, he knocks a tin can off the wall and it falls to the ground. Tin can weighs 0.2 kilograms and its velocity just before hitting the ground is 5.1 meters per second. Again, seems straightforward. One thing I'd check, the units, do they match what's in the question? And you can see the kilograms do, meters per second do, so we don't need to do any conversions. So this is why it's only worth 1 mark. Okay, it's fairly straightforward. Again, I would do some working out here. Next one, when the tin can hits the ground, it takes 0.1 seconds to stop moving. Calculate the resultant force. Okay, so we've got 0.1 seconds to stop moving. We need to calculate the resultant force. It's not giving us much in the question, so what we need to think there, if we've only got one value, that's 0.1 seconds, where are we going to get another value from? And because we're trying to calculate resultant force, we probably want to go to the question before, because one of the things about resultant force is you also need change in momentum. So if you know the momentum before, okay, and you know it stops moving, you know the change in momentum, okay, because let's say the momentum before is 100 kilogram meters per second and it stops moving, the change in momentum would be 100 kilogram meters per second, because the difference between 0 and 100 is 100. So that one, again, it should be fairly straightforward, but you've just got to refer back. Okay, so if you're given limited values, one way to check that is to refer back to previous questions. Now, this is the first one where we're not expected to do a calculation. So it says the tin can took 0.1 seconds to stop moving because the ground was soft, and they've highlighted that word. Explain what effect hard ground would have had on the resultant force. Now, nowhere in the aspect does it talk about soft and hard ground, but what it does talk about is impacts, and particularly things like crumple zones and airbags. So what you've got to do here, because you don't know about soft and hard ground, you link it to something you do know about. You wouldn't write about it in terms of crumple zones and airbags, but what you would do is use the same idea. Now with these ones, you've got to express it in terms of the resultant force equation. So you want to talk about increasing or decreasing the time taken for the change in momentum to occur. And you've got to decide what hard ground would do to the time it takes for the change in momentum to occur. So you're going back to the equation and you're not doing a calculation, but this part of physics requires you to constantly go back to calculations. Next one, George and Kate do an experiment with falling objects. They use two balls the same shape and size but different masses. Release the balls from the same height. Okay, so we've got different masses and we've got the same height. And find that they take the same time to drop to the floor. Okay. So George says, because the balls take the same time to drop, this shows that they have the same speed and kinetic energy as each other just before hitting the floor. Kate, but the mass of the ball affects its speed and kinetic energy, so they both would be different. Okay, comment on their conclusions, use equations to justify their answers. So we've got to separate it into two things here. Okay, so the first one is the speed. Now they both hit the ground at the same time, so that should allow us to conclude something about the speed of the objects. Okay. The second thing is about the kinetic energy. Okay, so it says George thinks the kinetic energy would be the same. Now, this is probably where I would be using an equation to justify. So, if you have a look at your kinetic energy equation, it's 0.5 times mass times velocity squared. And you can probably see from that, if you change the mass, you're probably going to change the kinetic energy, and then you'd be able to justify why the kinetic energy is either the same or different, depending on what conclusion you've come to. Blank page. Next one, still on forces. Alex goes for a bike ride, and the graph shows his displacement from the start of the ride changes with time. So the first thing is you really need to be familiar with displacement, so that's distance from a start point. And you can see you've got lots of different things. What I'd probably do with this before I even started looking at the question is just quickly annotate it. So in this one, we're accelerating forwards, and you can tell and you can tell they're accelerating because the gradient of this line increases. Then we've got a point where there's no displacement, so stationary, and then we've got a constant speed. Okay, again moving away, again goes stationary, and then we're going backwards, again at a constant speed. Okay, and then we can look at the question. Right, we've got to analyse it. One of the crucial things as you read this, you can tick more than one box in a row. Okay, so that's going to be important. Next one is quite a tricky one actually, for 1 mark as well. Which of the following sketch graphs shows Alex's velocity in regions C, D and E? So, first thing, crucial, you're only looking at this part of the graph. You're not bothered about B and A. So, what you've got to kind of do is relate that to a velocity time graph. So you've got to think what would match it. So they all show this stationary point, and then we've got various differences between them. So these ones have a constant velocity. These ones have acceleration because the velocity is increasing. So then we can probably narrow it down to two of them. And then what we'd do is we'd look at the type of velocity. So some of them have negative velocity. Okay, sometimes it's constant, and sometimes it's positive constant. Sometimes that velocity is decelerating, sometimes it's accelerating. So then by analysing each stage and by excluding ones that seem wrong for any one stage, you can come to a conclusion about which one works. And then here we've got to sketch how Alex's velocity changes with time in region A. So very straightforward, but it is worth 2 marks. So we're probably going to have to do something that justifies 2 marks, because they don't give 2 marks away for free. So you're going to have to really think carefully about region A. What's happening to the velocity? I think before we said it was accelerating. Okay, so how can we represent that? And we can also think about, does it start at 0 and time 0, because that might be something to kind of consider. Okay, and then on to the 6 mark question for the P4 section. So it's about how a car moves. So rotation of wheel causes the car to move forwards. Okay, yeah, that's fine. Okay, when the road is icy, it's more difficult to get the car moving. Use ideas about forces to explain how the rotation of a wheel makes the car move forward, and why it's more difficult to get the car moving when the road is icy. Now this is a typical OCR question, in as much as it has 2 separate parts to the answer, to the question, and then therefore to your answer. So what I would probably be doing is splitting it into 2. First part, in your answer, I would talk about how rotations of wheels makes the car move forward, and the second part, I would then talk about what happens when the road is icy. If you don't do both of them, you will struggle to get beyond about 3 marks. And it says you may draw labelled arrows on the diagram to help you answer the question. I would definitely be doing that, because what that does is it allows you to get some easy marks. Okay, so you can probably do that up there, draw some arrows, yeah, and you might not have to explain as much down in the writing section for you to achieve those marks. The other thing with these questions is to make sure you plan out some key terms. So if I was thinking about this, I'd probably do a little spider diagram. This is what the examiners recommend. And I'd probably think about some of the key terms. So I'm talking about movements, so I want to be talking about interaction, pairs of forces. So I'd be talking about things like the force of the wheel on the road, and then the force of the road on the wheel. I'd be talking, definitely, if we're talking about ice, we'd be mentioning about friction. And I'd be trying to explain that and why it has that effect. Okay, and I'd probably explain friction in normal conditions and in ice. And then if we do all those things, if we describe interaction pairs correct, and very importantly do the arrows correctly, and then explain the idea of friction, we're probably going to get in that level 3, the 5 to 6 mark box. Okay, so now on to the next one. Okay, we've got Anna investigating resistors. And the first thing is a nice one, okay, so it's just completing a circuit. So she connects a resistor to a battery, an ammeter and a voltmeter to measure the resistance of the resistor. Complete the circuit that she should use. So one of the key things is that we have a battery already, we have a resistor already. So this question is essentially asking us to draw in an ammeter and a voltmeter. And the thing you've got to remember is, are they connected in series or in parallel? And the crucial thing is they're trying to measure the resistance of the resistor. So if something's connected in parallel, it's going to have to go round here. Okay, if something's connected in series, that should be much more straightforward. 2 marks for that, which is nice. Okay, it's a nice introduction. Next one, the current she measures through the resistor in part A is 0.2 amps. She then makes changes to a circuit using the same battery and resistor. Okay, so now we've got 2 resistors, okay, but they're identical. So the following circuits all use resistance and batteries identical to the ones used in part A, and that's important, so we know that these are the same. So it then asks what is current 1, so the current's measured here, although it doesn't really matter, it'd be the same all the way around. Put a ring around the correct value. So for this, what we're essentially being asked is, do you know the rule for resistors in series? That's what it's asking us. And because it's only worth 1 mark, it's quite, it's going to be quite straightforward. Okay, that's all they're asking. Do you know that rule? And if you do, circle the correct value. This time, they're asking something slightly different, which is, do you know the rule for resistors in parallel? Because here we've got 2 resistors in parallel. Okay. Then it's this, in this next bit, I'm sorry if this has gone a bit weird, it's just because the iPad ran out of charge. So in part 3, got back to 1 resistor, and now we've got 2 batteries. So again, what we've got to do, we've got to use our rules. Again, it's very important you know your rules in electricity for when you increase certain things in either series or parallel, what happens. And then we move on to this question. So got a circuit with resistor, LDR and a battery. Okay, and we can see those. And it's asking us, she shines the torch on the LDR, the voltage across the resistor increases. So the voltage here across the resistor would be increasing. So then we've got to explain it out. And so this question is probably targeted at high grade. So what you'd probably start with is the effect light has on the LDR. So we'd start with light on the LDR. What effect does that have on it? And then we'd try and build it from there. So if it lowers the resistance or increases the resistance, we can then link it to our equation, which is given earlier. And that should then help us to kind of explain what's happening in terms of resistance, voltage and current. You might need to rearrange that equation. Alright, I've got... Okay, and so on to question 5, a 6 marker, and hopefully not a bad one. targeted up to grades A. So what we've got is we've got Pat and Chris setting up an experiment to find the relationship between current and voltage in a filament lamp. When they increase the voltage, the lamp grows brighter. They record the voltage across the lamp for different values of the current. Well, that's a hard way of saying they record the voltage and the current. So here you can see we've got voltage and current. The current is increasing, and it's increasing in a linear fashion, so we've got equal intervals. And then we've got the voltage, which is also increasing, but that doesn't seem to be equal intervals. We've got a gap of 1.2 here, about 1.9 here, and I think 3.8 here. Okay, so it's increasing, but in a different way. Sorry, that's 1.3. Okay, so we've then got a couple of statements. Pat says there is no correlation between the voltage and the currents, and Chris says the resistance of the lamp filament does not change because it's the same piece of wire all the time. Okay, so the resistance of the lamp filament does not change. Comments on the statements, use the data to justify their answers. So you'd probably start off with Pat's, because Pat's is an easier statement. So again, it's this OCR classic of having two sections. Okay, so we'd have Pat and we'd have Chris. So Pat says there's no correlation, so you'd use that data to explain if there is or there isn't a correlation, and what type of relationship it is. So I think maybe Pat's getting confused between a linear correlation, where it's a straight line, and then a non-linear correlation, or not proportional. And that is still a relationship, a correlation, but it might not be a straight line. Okay, so we wouldn't see that kind of thing. What you might want to do with a question like this is kind of sketch out what you would see. Then we'd move on to Chris. So Chris says the resistance of the lamp does not change. So firstly you've got to decide if he's right or if he's wrong, and then we'd try and explain why the filament does change its resistance or it doesn't. What you'd probably want to think about is temperature. So current's increasing. What would happen to the resistance of that lamp when you get increased current? The other thing you'd probably want to do is this part of the question that says use data to justify your answer. So we can actually work out, using our equation, some resistances from here. So we've got different values, pairs of values, so we can work out some resistances and actually see if Chris is right or if he's wrong from that, and then try and explain it with this idea of temperature. Okay, and then on to probably the hardest question on this. Okay, electric motors are notoriously difficult. So it says lots of devices use an electric motor. Diagram shows the main feature of a motor, and we've got a force here, we've got the commutator, and then we've got our loop of wire going around here, our coil of wire, and we've got our magnet, which then creates a magnetic field, and it's got the magnetic field lines, which is quite helpful. The arrow on the diagram shows the force acting on side AB. Okay, so between A and B, when a current flows in the coil. Draw another arrow on the diagram to show the force on side CD. Well, what we've got to think is, if it went in the same direction, something very strange would be happening. So we'd have to think, if this end moves up and then moves round, what ways C and D going to move? Okay. And then it asks us why there are forces on sides A and B and C and D. So then we've got to think about, why do we have, like, why do motors work? Okay. And from the diagram, we've actually got some of the key fields of motors. So we've got current moving around, we've got a magnetic field, so we've just got to link that all together. Quite a bit of the information actually for this is up in here. And then a hard one, very hard one, explain the function of the commutator in this motor. Okay, so what you've got to do is try and explain why this is here. And with this one, it's 3 marks. Probably each point is going to be a separate mark. Okay, so you want 3 reasons essentially. Tough question, that last bit. Next, moving on to P6. I know my class has probably seen this one before, but it's worth going through it. Okay, so teacher sets up a demonstration experiment. She uses a radioactive source to measure how its activity changes during the lesson. She handles the radioactive source very carefully to avoid the risk of irradiation and contamination. Explain why the contamination from the source is more hazardous than irradiation from the source. So you've just got to think straightforward. Okay, so the first thing is probably with this, because they haven't given you the definitions, I would start at the very basics. So I would tell them what contamination is, and I'd tell them what irradiation is. So if there's no definitions, that's what I'd go with first. And then I'd try and explain why this is less dangerous than this. And then we should have got the 2 marks quite easily. Next one, we've got a graph, and it looks like a classic half-life graph. We've got a decrease, it looks like a curve, okay, but a couple of points don't quite fit. Okay, so it says complete the curve by drawing a curve best fit to show how the source decays. So the first thing often to do is kind of to just sketch with your finger maybe an approximate curve. So something like this, and we want as many points above the line as below, and if there's anything that seems anomalous, there isn't in this case really, okay, would want to get roughly as many points above as below. When you do sketch graphs, please don't make it sketchy, so do one clear line. The way I often do these is by bending a 30cm plastic ruler, shatterproof one. So kind of align it and then just draw along it. Use the graph to estimate the value for the half-life of the source. So you'd use your line of best fit, and then it starts off 125. So we find half of 125, go across, and then go down, and we should have the half-life. Now it's very important you do it accurately. So if it ends up being here, then I would make sure that you say 6.5 or 6.2 or something along those lines. Don't just go to the nearest whole number, because it might not be right. Then we've got a nice question. What is background radiation? Simple, straightforward, just a definition. We don't need to go to great detail on that one. And then we get a question about calculating half-life. So the background radiation in the laboratory is 20 counts per minute. After how many half-lives could this source be considered safe? Okay, so we'd go back to our graph. Okay, and would find out how long it takes to get to 20 counts per minute. So, for example, first half-life starts off about 125. Next one would probably be around about 63. Next one would be half that, so about 31, still not safe. And next one would be about 15, 16, okay, depending on how you round it. So then you just add up the number of half-lives, and the half-lives are represented by the arrow. We've been through this one before. Okay, and then we're on to a question about nuclear fission. Now it's very important, firstly, immediately, it's nuclear fission. Don't get it confused with nuclear fusion. It's got a nice diagram that should help to remind you what's happening. Okay, so we've got a nucleus absorbs a neutron and then splits it into two parts and releases a number of neutrons. So they're here, and the fragments are there, and the original uranium is here, and the incident neutrons there. So how does this process produce a chain reaction? So we've just got to use information from the diagram to explain how we'd get a chain reaction. So it just requires us to know what a chain reaction is, and then a quick scan of the diagram should tell us what happens. Next one, how do the control rods in the reactor control the speed of the chain reaction? This one, there's no clues here, it's just something we've got to know. So we need to know how control rods work to control the speed of the chain reaction. What can they do to stop this reaction continuing? If you know A part 1, you probably know A part 2. Then we come to some decay equations. So these are quite nice if you can remember the rules. So this is worth 3 marks, which is, you know, a fair amount. It could make a difference between one grade and the next up. And what we've got is we've got one decaying and producing alpha radiation, one decaying and producing beta radiation, and then it gives you kindly the element that's formed. So just from knowing the elements, and remember you'll have a periodic table at the end, you should be able to fill that in straight away just from the periodic table. And again, you can do the same with barium. Okay. Then what you've got to do is you've got to make sure you can remember what an alpha particle is, how we notate it, and what a beta particle is, and what notations we use at the top and bottom. And then you work out the number of neutrons and the number, the relative atomic mass. What you've got to make sure is that if you write a value here and you write a value here, both them together should equal that value. Same, you've got a value here and a value here, both them together should be that value. Next we've got Ali, who's a bit worried. Worried about the effects of a nuclear accident. He knows that the risk of an accident at the power station is much less than the risk when driving his car. Suggests why Ali is concerned, even though the risk is low. And this is all kind of classic OCR risk and effect. So some things we might be thinking of are perceived risk versus actual risk. So perceived risk is what you think the risk is versus the actual risk, the actual chance of something bad happening. And then the other thing you've probably got to think about when you're assessing risk is the consequences. So what's the consequence if there is a nuclear accident compared to the consequence if there's a car accident? Okay, and then maybe things like control of risk. You could even go with like social things, so like considering like, you know, his area and the effects it might have on that. and then on to the final question, which again it's a nice question, okay, and if you've been following so far, it's very, very similar in its wording. Okay, so Priya is going to work in a laboratory where radioactive sources are used. She knows that radioactive sources can be dangerous. Her supervisor has reassured her that the risk is low if she follows the safety procedures. Here's some safety procedures. She's got 3 of them here. Disposable gloves, long-handled tongs, and a monitoring badge. Right, so again, it splits into 2 parts. What are the risks from handling radioactive sources, and how do these safety procedures reduce the risk? So again, what you want to be doing for this one is splitting your answer into 2. So what are the risks from handling radioactive sources? So we think about the obvious things and we'll try and explain why they happen. And then the safety procedures, what we want to do is basically mention each of these and explain how they help to keep Priya safe. Okay, so I probably have a sentence on gloves, a sentence on tongs, and a sentence on the badge. And if I've done the risks part, okay, and why radioactive sources are risky, and I've covered each of those, then really they can't do anything but give me a 6. Okay, and that's the end of that walking, talking